The next is effective nuclear charge. We know that a pair of unlike charges attract to each other, somewhat like how opposite magnetic poles attract. Positive charge attracts negative charge, and within our atom, our positively charged protons attract the negatively charged electrons. The protons are concentrated in the center, and the electrons are all around it. The net positive charge that the electrons feel from the nucleus is termed as nuclear charge. However, as previously mentioned, these electrons are not evenly distributed around the atom. While it is true that the nuclear charge on every electron should be the same, given that the same number of photons is acting on every electron, we will still see electrons experiencing a greater nuclear charge than others. This is where the word effective becomes very important. The effective nuclear charge an electron may experience is different from the nuclear charge due to a phenomenon known as shielding. As an analogy, imagine that you are sitting in a classroom facing the whiteboard, and it happens that the dude in front of you is particularly tall. You can make out the dandruff in his hair, but you cannot see some parts of the whiteboard because he's blocking your view. This is what's happening. Let's say now you are an electron experiencing a nuclear charge. If other electrons are closer to the nucleus, they would shield you away from the nuclear charge. So the effective nuclear charge you will experience will be lesser. In studying trends, we are typically interested in the effective nuclear charge on the valence electrons. This is because we remove or add electrons, it is always involving the valence shell, the outermost shell. How do we calculate effective nuclear charge? The formula is simply given as follows, where Z star equals to Z minus sigma, where Z is the nuclear charge, in other words the number of protons, and sigma is the screening constant, and there are several ways to calculate it. In its simplest form, it is just the number of electrons in the inner core, as these are the main contributors to the shielding effect. But this is assuming that all electrons in the inner shell shield nuclear charge, while those in the same shell does not, because they are all at the same energy level. This assumption should be sufficient for most part of H2 chemistry.